So yeah, let's start. So yeah, our company deals with such EDA tools and the simulation software. So currently we are going to explore one of the tool called Synopsys QuantumATK, which is mainly based on DFT, that is density functional theory based nano level design and simulation tool, in which one can create and simulate atomic structures. So this quantum ATK mainly written in two languages, that in Python and C++. Most of the simulation engines are written in C++ language, like DFT, LCO, DFT plane wave, or the semi-empirical force field, their potentials, basis set, etc. And most of the automated part, like machine learned force field for crystals, for defects, for generating the automated script, etc. These kind of parts are written mainly Python language. So these are the four important pillars of this software. These are the simulator engines actually. The first one we have is density functional theory. So it is one of the approximation method, as you all know, that we use to solve the to solve the Schrödinger wave equations and electron body equations. So for DFT, we have mainly two basis set, that is a linear combination of atomic orbital basis set and plane wave basis set. In all the basis set also you can choose the pseudo potentials as well. And second, we have semi-empirical tight binding. Yeah, one more thing. If you have any doubt during my talk, you can interrupt me, right? Yeah, second we have semi-empirical tight binding, which is for larger structure simulation. So in this, we have mainly three methods, that is of Slare-Coaster method, extended Huckel method. Also, you can use the density functional tight binding, and even you can define your own method as well, extension method. Then we have classical and machine learned force field for such phenomena like molecular dynamics, Hooke's phenomena, etc. So atomic scale simulation using classical potentials such as bonded, reactive, force field, pair potentials and other parameterized interaction molecules for atoms. We have this classical force field. And then we have non-equilibrium Green's function, which is for device simulation. This module is for nanoscale device and transport simulation. Using non-equilibrium Green's function methodology, you can use either DFT, LC, or the semi-empirical model for describing the Hamiltonian of the matrix. Also, you can see here this term, machine learned force field. This is something very unique feature of quantum ATK, that which provides accuracy near to the ab initio for larger elastic system sizes and the dynamical simulation time, which greatly exceeds those which are inaccessible to DFT. So yeah, it gives you all the simulation engines, whether you are dealing with the molecules, fluorescence, zeolites, organic molecules, or the bulk configuration devices, transmission properties like etc. So it is an effective tool. Any kind of users, like if you are just about to start these kind of simulation in this kind of software, so you can directly start using this tool due to its interactive UI. If you are the experienced one as well, also you can use the uh, Python scripter to make your script even more effective. But although if you do not know Python, it's not necessary. You can directly use the builder module and the workflow that we will show in the live demonstration. It gives you the synergetic solution, properties like electronic, optical, mechanical, and thermal, and transport properties for the devices you can calculate. Also, you can integrate this tool with other TCAD tools. So if you are going to set all the parameters accurately, you are going to get the results very similar to the experimental one. So these are the some major applications where you can use this software. Here you can see you can deal with the molecules. Suppose if you wanted to find the behavior of molecule under different vibrational modes under the influence of electric field or their reactivity, for which you can use the Cosmo RS, which is loaded in the software. Also, you can create the surfaces of the bulk configuration to study the phenomena, like if you wanted to calculate the work function or the electronic surface structure, Fermi surfaces, etc. Also, we do have the plugins to create the interface between different structures, multiple structures, to calculate the properties such as Schottky barrier height or the van der Waals force like DFT2, DFT3, etc. you can introduce, which is applicable in such applications like sensing, biosensors. If you are creating a biosensor, you can do simulation in this as well. Also, here it is device configuration. After adjusting the perfect width and length, you can create the device from the bulk configuration. So first you are going to create the structure, whether it can be the molecule or the in the bulk configuration. Then after that you can convert that structure to the device configuration. And to calculate the device properties such as IV characteristics, their phonon transmission spectrum, any transmission property you can calculate for the device. And also you can deal with the complex material. We do have the molecular builder to create such complex structures. Also you can deal with the polymers and composites. For nanostructures, we do have some plugins like you can create the nanoribbon, nanowire, nanotube, nanoparticle, etc. So here it is the basic workflow that how you are going to propagate for our properties. So first we are going to create our structure using the builder tools. Also, you can import your structure. This software also have its own inbuilt data set, which covers the versatile, means a big palanthor of these structures. Also, you can manipulate this structure after fetching from the inbuilt database. Although it also supports the online database as well. So you can directly import the structure from the online database, whether in any form of file like CIF, VAS, XYZ, etc. Then we are going to set up our all the calculations, like if you wanted to calculate the band structure, total energy, Fermi plot, etc. Yeah, here it is the important part. After setting up the calculations, you are going to submit this simulation in the job submission module. In this, we are going to fire our simulation. And after simulation has been completed, we are going to get the result in the form of HDFI file in data module. So here you can see which simulator engine we should use depends on the number of atoms in our structure. So if your structure contains up to 10 to the power 3 atoms, then you can proceed with the density functional theory plane wave calculator simulator. And beyond that limit, we do have DFT LCO, that is of linear combination of atomic orbital. Even though also for the device, you can use the non-equilibrium Green's function with the DFT LCO or the sparse Green function. Similarly for semi-empirical. And beyond that limit, we have force field and the machine learned force field. After that, for bigger structure, you cannot do the simulation, but you can integrate with other tools like TCAD, SPICE, etc. Yeah. So these are the two basis sets that we have for DFT, that is of plane wave basis set and the linear combination of atomic orbital. So plane wave is conceptually simple, especially unbiased, but at the same time, LCO does not neglect the vacuum. It LCO neglect the vacuum, and the plane wave basis set does not neglect the vacuum. For the calculation of Hamiltonian matrix, it considered vacuum same as matter. So which makes LCO much faster than DFT plane wave. So here you can see we have done the simulation using the exchange correlation family of hybrid functional. This feature is also loaded with this QuantumATK software. So here you can see when we are using DFT LCO with the hybrid functionals, with respect to system size, the computational time is just linear. At the same time, for the DFT plane wave, we got the computational time which is proportional to n3 log n, which makes DFT LCO calculator 10 to 100 times faster than DFT plane wave. But DFT plane wave gives you the higher degree of accuracy, which is applicable in some cases. But DFT LCO also have its own application area, which is even more effective than the plane wave basis set.
Sir, what are hybrid functions?
Yeah, is there any question?
No, Tushar, you can continue.
So yeah, for the devices simulation, we have DFT plus non-equilibrium Green's function method. So here you can see I have tried to show the device. This is the central region. This is the left electrode, which is the source. And here in the right side, you can see it's the drain. Also, you can create the 2-probe device, 3-probe device as well. So after selecting the correct vices and gate, you can calculate the properties such as resistance, capacitance, IV characteristics, cell dissipation, self-heat dissipation, stability, quantum efficiency, which is applicable for solar applications, etc. So here you can see for the battery, which is one of the applications, how you can create the structure and simulate in this software, like lithium ion diffusion in cathode material. Using multi-model, we have done the simulation. First, we are going to create the structure. Also, you can use the nudge elastic band to calculate the properties in the transitions. Also, here you can see some advanced analysis, that is harmonic transition state theory, adaptive Monte Carlo method, or the force biases Monte Carlo method. There also supports the constraint Monte Carlo method as well. So these are the some major applications where you can use this simulation tool. This helps in designing and optimizing a new semiconductor material and device before physical fabrication in lab. So it will significantly reduce the development time and cost. For the batteries, as I have already told you, that you can calculate the lithium ion diffusivity. Also, you can calculate electrochemical stability, capacity, thermal stability, etc. For the solar and fuel cells as well, you can calculate the band gap energy absorption spectra, carrier mobility, charge carriers, photocurrent, quantum efficiency as well. Similarly, you can deal with the polymers at the atomic level. You can try to reduce the you can try to calculate the thermal stability, its reliability for the polymers. Similarly, you can deal with the catalysis, for which we have the thermochemistry analyzer that you can use to study, in which you can study the graph between Gibbs energy. And also, you can deal with the metal ceramics and the glasses. So yeah, let's recap what we have discussed till now. First, we are going to create our structure, simple, and then after that, we are going to set up our calculations. Whether you can use the DFT LCO, plane wave, semi-empirical force field, which is depend on the on your structure and the property that you wanted to find. After that, we are going to run the simulation in the job manager. And once the simulation has been done, we can analyze the result using some advanced analysis tools that we will see in the live demonstration. So yeah, question arises, why do we need the machine learned force field? See, in industrial problems, sometimes we have to tackle with the such simulation which contains even more than 10,000 atoms to be simulated. So to find the properties or for such phenomenon like complex structure generation, mechanical properties, thermal properties, electron phonon scattering, here you can see, we use machine learned force field because we cannot use our existing calculator like DFT or the plane wave or LCO calculator due to TAT limitations, that is turnaround time. Also, it will reduce the some quality, which is the quality of result. So machine learned force field is nothing but when we apply the machine learning model in the conventional force field. And the machine learned model that we have in this software QuantumATK is MTP, that is moment tensor potential. So you can generate you can by using the machine learned force field, you can generate this data of MTP, that is moment tensor potential, like energy, stress, forces, and then after that you can use that data for to calculate such analysis like molecular dynamics, vibrational modes, etc. So here you can see I have tried to compare the accuracy with respect to computational time of different simulator engines. So for the classical force field, we do have very less accuracy, but the application, it covers also the big application area. Also, here you can see its computational time is very less. When we move forward, we have semi-empirical simulator, which gives you the very higher accuracy with respect to the classical force field, but its computational time is also high. Yeah, here it is computational cost, which is directly proportional to the computational time. Then we have ab initio method. which gives you the higher degree of accuracy like LC or the plane wave. But its computational time is also very high. But at the same time, for machine learned force field, it gives you the accuracy which is very similar to the ab initio method, and the computational time is also very low. Here you can see, which is very parallel to the classical force field. So here I have shown one example that is of hafnium, which contains 96 atoms, and we have done the 50 molecular dynamics steps on 16 core system. So MTP, that is of machine learning force field, just take 10 seconds. At the same time, when we try to simulate for the ab initio method, that is of DFT LCU, it takes 3 hours, 21 minutes and 27 seconds. But the accuracy for both of the cases is similar. So here you can see how you can take advantage of machine learning force field once we have the data from the DFT initial data. So these are the some applications of machine learning force field. Here you can see you can generate the amorphous structure for PC RAM. You can also deal with the multi-layer stacks like build and optimize complex spline and amorphous interfaces and multi-layer stacks structure for semiconductor development and applications such as high K metal gate and MRAM, that is magnetic tunnel junction engineering. Also, you can deal with the crystallization and amorphization. You can study the NS long crystallization and amorphous process with the machine learned force field molecular dynamics in large scale system. You can simulate the thermal conductance using machine learned force field with the reverse non-equilibrium molecular dynamics simulation for developing and evaluating cell fitting and the cell dissipation devices. Also, you can deal with the surface processes like nuclear deposition. So the GUI of this software is called Virtual NanoLab GUI. Here you can see the different tools. This is this screenshot that I have pasted here. Yeah. So these are the some advanced analysis that you can perform. Here I have listed only few. So the first one is molecular dynamics. So you can calculate the diffusion coefficient, phase diagram, elastic medullae, radical distribution, angular distribution, thermal properties like specific heat, as I've already mentioned, mechanical properties like Young's modulus, stress strain graph. That is, you can also fetch such properties. Then we have optimized geometry. You can find the most stable and the atomic position with the system by minimizing the total energy, which will translate to determine the key properties like bond length, bond angle, and overall molecule geometry. Then we do have the dynamical matrix, which you can use to calculate phonon band structure, phonon density of state, Raman spectra, deformation potential, vibrational mode, dielectric tensors, etc. And so on. We have a Hamiltonian derivative, charge point effect, adaptive kinetic Monte Carlo method, uh, time stamped force bias Monte Carlo also, grain boundary scattering, magnetic anisotropic energy, polymer polarization, suspectibility derivative, which is part of optical spectrum. So here I have listed all the compatible characteristics that you can calculate, like band structure, Bloch state effective mass, electron difference density, Gilbert damping, external potential, exchange correlation potential, Heisenberg exchange, harmonic transition state theory, event, etc.
Yeah, Tushar,
Also,
just hold on. Just hold on to the
devices.
previous slide
Yeah,
because there are so many properties which we can see over there. Just hold on to the previous slide, previous one. So we have got the
yes, sir.
elastic electron density analysis, electron difference density, electron localization function, electron phonon coupling, RT potentials, Fermi surface, hard band structure. Fine. And please go to the next one, chemical potential, band structure, current density. These are mainly the electrochemical related properties. Go to the next one. We have got inelastic transmission spectrum, IV curves, local band structure, and local density of states, local stress, mobility, molecular energy spectrum, Millikan population, photocurrent, piezoelectric polarization, partial electron density, partial charges, Raman, dose, partial dose, spin transfer, total energy, transmission, even states, vibrational mode. Good. Yeah, please continue. So there are a whole lot of properties which can be estimated, right?
Yes, sir.
When
Actually, all the mechanical and electrical property, although if some properties are
Hmm,
not there, you have the Python script that you can define from these
correct.
basis properties, right?
Great.
Suppose if you have the data from the IV curve plot, then you can use this data to calculate the capacitance, resistance, etc.
Good. Yeah, please go to the next.
Yeah, so we were submitting the job to the module called Job Manager. So here it is the details of Job Manager, that how we can simulate the job simulation. So this is the part which I think I will show in the live demonstration. That would be great.
Hmm.
So, but for the remote modes, let me share. These are the remote modes that you can fire the job remotely as well. For the remote modes, it supports for PBS Slurm, SGE, LSF, and even you can perform the direct execution, whether your remote machine is scheduler or non-scheduler based. You just have to define all the environment parameters like SSH, username,
Hmm.
password, etc. Then you can run the job remotely as well. So these are the system requirements. It does not need any external library beyond the standard OS packages. It comes with the ATK calculator and the VNL GUI available for Microsoft and Linux, only 64-bit operating systems. It supports the MPI parallelization for Windows and Linux. The license type is floating. So simultaneously, you can perform 5 DFT simulations, 5 materials, 5 force field, 5 machine learned force field, and 5 devices simulation as well. So in total, you can perform 25 simulations simultaneously, whether on the local machine or the remote machine. But the condition is those systems must be connected over the same LAN network, local area network. So currently, these are the institute that are using this software for their research purposes. Here I have listed like IISR Bhopal, IISR Kolkata, IIST Trivandrum, Triple IT Delhi, Triple IT Allahabad, DTU Delhi. These are the more different IITs and NITs are using this software like GMI Delhi, IIT Patna, IIT Roorkee, Ropar, GNU Delhi, NCL Pune. Yeah. So till now, do we have any doubt or can we proceed with the live demonstration?
Yeah, any doubt from the participant, please you can ask the speaker. Otherwise,
Yeah.
we'll move on to the live demonstration. Yeah, you can vocally ask or you can either put up in the chat box if you have any question. Okay, Tushar, please go ahead.
I think there are no
Devaparna,
doubts, but although if you have any, you
uh,
can share even in the
Devaparna,
live demonstration.
Devaparna, you had raised a hand. You have any question?
So I would like to know partial charges. How can we calculate partial charges using quantum ATK? Just basis of.
Yeah, I will create the workflow for that. First, we will move to the builder that how you can create any structure. Then
Okay.
for any particular structure, we will try to calculate the partial charges, right?
Okay. Okay.
Okay, so this is the GUI of this software QuantumATK, which is a virtual nanolab GUI. On the left side here, you can see these are the different tools. Currently, we are at the project module. You can define your own project just by clicking on plus sign. Then we have the data module. After the simulation in Job Manager, you are going to get the results here. All the results, log file, their Python file as well, and the results file, all the file. Here it is the builder module where we are going to create our structures. This region where we are fetching our structure is called stash. This region, this is the stash toolbar. This is the region where we are seeing the structure in the 3D view, which is the 3D viewer. Also, these are the different plugins that you can use to create this structure. Here it is. If you click on here on plus sign in stash toolbar, here you can see this is the database from database. This is the inbuilt database of the software, which covers the big palanthora. Here you can see you can deal with the molecules, crystal, fluorescence, zeolites. Yeah. So it covers the big palanthora. Here you can see we can deal with the molecules, crystal, fluorescence, zeolites, monomer, even ground state elemental crystals as well. So let's say if you wanted to fetch any structure, you just have to click over here. Let's search for any structure. Let's say gold. Here it is. Here you can see the detailed symmetry of that details of this structure, like its chemical formula is AU. This is the face-centered cubic structure with the lattice A of 4.07852. Space group is 225. Crystal symmetry is cubic. Parasan is CFN. Here you can see all the details. So let's say if you wanted to work on this structure, then click on plus. Here it is how that you can fetch the structure from the inbuilt database. Also, if you are not able to find your structure in this inbuilt database, then you can proceed with this online database. Here you can see. This is the online database. So for online database, mainly we have
Materials.
two. This is the crystallography open database and the materials project.
Great.
So here what you have to do, you just have to select the elements that you wanted to introduce, that you want to be in your structure. Then it will fetch all the structure with the possible combination of these elements. Let's say if I choose carbon, nitrogen and oxygen, and if I click on search here, you can see it is searching in the database. Actually, it is the basic practice like how other databases works, whether it is the materials project, COD or any other data. Yeah, sometimes this thing happened when the any database, actually these are the online database are under maintenance. So sometimes it happens when they are under maintenance. So currently COD must be under maintenance. That is why we are getting this error. Because weekly they introduce some few new structure to their databases. So currently we cannot proceed with the COD.
It's fine. I think we can download it from their server itself and then can open it in the interface as
Yeah,
well, right?
yeah, directly you can even fetch the CIF file as well. Here you can
Uh,
see. Let me check if we have any file.
it is something like a thing we do it in a Burai software. So we are using the Burai to do these kind of thing, materials modeling. So I can see it is almost similar to that. But as you have mentioned that it has got another capability like a ML based calculation, which is more accurate. So we'll see that. Is it a student version? What are the pricing for the institutional license? Yeah, within I think Deepak or Tushar will share the information in the meanwhile. Let us first see how the scientific things are going on. Okay, Riven?
Sure, sure. After just introducing the builder tool, I will proceed with some of the test cases
Sure,
that how
sure.
you can use this tool, and we will analyze the results even.
Okay,
Just a second, let me check for any CIF file that how we can import.
sure.
Here it is. Yeah, the materials project is currently working. Yeah, let me download the CI file. Let's download for primitive cell. Okay, now we can import that file. Here it is, SiO2. Open. Yeah, so here it is. Not just the CIF file, all the file format it supports. Let me show you whether it is HDFI file, which is the ATK file itself, .NET CDF file, CASTIF file, XYZ file, CAR file, ASE file, FHI, MBN. Almost it covers all the kind of file. Even you have the raw data, you also you can import that structure. You just want, we just want the lattice information and even the Cartesian coordinate and the atom names. Then even with that raw data, you can put that thing in the scripter and can import the structure. So yeah, this is how you can import the structure from the inbuilt database, from the online database. So there is a case, suppose if you are not able to find a structure in both of the databases, then you can proceed with then you can create your structure from the scratch. For this, you have this crystal builder or the new configuration. If you click here, so it gives me the hydrogen atom. If you stay your cursor over here, you are going to get the information about Cartesian coordinates. Here you can see it is the molecular builder. So if you click here, then you can select any atom, any element from the periodic table. Let's say if I choose carbon, you can choose the hybridization as well. So if I click here on any atom, it will change to the sp2 carbon. So here you can see. This is the simpler structure that I have created, which is benzene. So this is how you can even create any complex to complex structure in using this builder module. You can see this some inbuilt data to create any structure. Here you can see, then you can fetch the structure as well, ligands, halogens, simple rings as well. If we disable this option, now this is benzene molecule that we have fetched in our builder. Let me introduce some of the plugins that we have. Here it is the AMF cantilever tip, which supports the bulk configuration. Yeah, here this is the bulk configuration, which means it repeats itself throughout the cell in A, B, and C direction and depends on the property. Let's say if I drag this here in AMF cantilever tip block, if you click on build, here you can see we have created the structure of AMF cantilever with the spheroid clip method. Here you can see. And if I talk about GUI, here you can see we can just delete the structure by just clicking right click. You can define the base height and the taper height as well. Similarly, you have the amorphous builder, pre-builder. You have to just write the formula here, like it is written SiO2 and the number of atoms that you wanted to include in your structure. Then you can click on build. Here you can see we have fetched the structure, amorphous structure of SiO2. Here you can define the density. And the also you can define the jitter factor, which is nothing but something directly proportional to the discontinuity of this structure. If higher the value of jitter factor, then you are going to get the more disordered structure. Also, you can create the alloy. Here you can fetch any element. You can select any element from the periodic table. Here you can see. Also, you can define the structure type like Hazeler X2YZ, XYZ, ZXY, or the type 3, type 1, type 2, etc. Then if you click on preview, currently we are at preview mode. On the red background, you can see if I click anywhere, it will dismiss that structure. If we can click on create, now we have created the Hazeler alloy. Also, you have this isohedron builder, interface builder. So let's create the interface between any two structure. Let's say for the same element gold, if I wanted to create the interface, and let me fetch another structure that is silicon. Here we have to just put the uh, bulk configuration. Here you can see we have created the interface. Also, you can increase the length accordingly. You can define the layer settings. Here you can see you can define the surface cell settings with respect to the mean absolute strain and the number of atoms. If you choose the bigger one, if I click on apply, here you can see we have created the interface between gold and the silicon. And to stabilize the structure, you can use the DFT LCO calculator, and you can enable the van der Waals force or the band correction method to create the stable structure. Yeah. Then we have nanoparticle builder, in which you have to put the element for the core and the shell. Let's proceed with these are same structure. I want a gold particle in which my core as a gold and the shell as a silver. Then we click on create. Here you can see we have created the nanoparticle. So yeah, there are some other plugins that you can use in a similar way. Also, you can create the interface between multiple structure. You can also create the grain boundary structure. Yeah, for the adsorption, let me show you. Let's create the nanosheet. Here you can see in the plugins, we do have nanotube, crystal builder, nanoribbon, nanosheet, or also you can create the magnetic tunnel junction structure. If we click on nanosheet, you can select the elements. Let's proceed with the default parameter that is of graphene. Yeah, here it is built. Also, you can repeat the structure. You just have to define the multiple in any direction. Let's say in the C direction, if I wanted to multiply that structure 5 times, then here you can see I have put it 5. Click on apply. Here you can see we have created the graphene sheet. Let's import some molecule for the adsorption. We can choose water. Here it is, the water molecule. Before adsorption, if you want, you can you can optimize that structure. Although, let me disable the geometry selector. Yeah. Here it is, the adsorption option. This is the adsorption site, and we want to absorb the water molecule. We click on recalculate the adsorption site. Here it is calculating. Now we got the sites. Here you can see on top bridge 1, 2, 3 different sites that we got. So here you can see you can define the position of water, whether it can be the on site 2. These are the breach cases. Distribution also you can define whether it can be the random, quasi-random, surface grade, site 0, 1, 2, 3, occupancy, height, surface grade, etc. So where we can use such phenomena, like if you wanted to calculate the hydrogen redox reaction, for such cases you can use this adsorption. You can calculate even the energy, adsorption energy. So here it is about the adsorption tool. If you click on create, the structure will be in our uh, 3D viewer. So let's take any simpler structure to proceed with the calculation parts. So let's say if we wanted to calculate the properties for that gold bulk configuration. So by clicking on that sign, you can take this structure to the workflow. Now, these are the calculators that we use to calculate the properties. We have the LCO calculator. You can use the device, which is for device configuration. This is the plane wave calculator. Then we have the semi-empirical calculator or the device semi-empirical. Then we have force field calculator, and this is GW calculator, which is for many body perturbation theory. So let's say if we proceed with the LCO calculator, so these are the parameters that you can define. If you wanted to introduce the spinotonics in your structure, then you have the option of polarized, non-collinear, non-collinear spin orbit, etc. This is the exchange correlation family that you can define. Whether you can choose the local density approximation, global gradient approximation, meta global gradient approximation, hybrid. Also, you can define your custom exchange correlation family in that descriptor. So let's proceed with the gradient approximation. These are the pseudo potential method, whether you can proceed with the non-consuming or power method. These are the pseudo potentials: FHI, HGH, OMX19, pseudo dojo, SG15. Here it is. This is the basis set. Yeah, in the numerical accuracy, you have to choose the occupation method which depends on the structure type. So although the inbuilt function of the software can choose the this occupation method directly, automatically, but still if you wanted to change, we have options of Gaussian smearing, Mathesfield Paxton, gold smearing, any method for the numerical accuracy you can define. This is the broadening you can define. The density mesh cutoff. For the k-point sampling, we do have the density and the Moncost pack grid for this bulk configuration. So you can define the k-points, low, medium, high. Also, you can define the manually. Let's say 532. Here you can see. So on the second block, we have exchange correlation family. This is predefined functional. Currently, we are using the Pedro-Briggs and Arabzon exchange, that is PBE. These are the different predefined functions. So you have to choose accordingly what properties that you are working on. Directly depends on the property and the structure. Also, pseudo potential that I have already introduced. Also, you can define the basis set in that path. Let's see if I wanted to proceed with the polarized, then we can proceed with the FHI. Here on the basis set, you can define double zeta polarized or the single zeta polarized, or the single zeta or double zeta or the tier one. Let's say if I wanted to proceed with the single zeta. So after defining the calculator, now we comes to the analysis part. So these are all the properties that you can calculate. Currently it is the bulk configuration. So let's say if you wanted to calculate the band structure, then we can fetch the band structure. So if you double tap on any block, here you can see the details. That is the Bernoulli zone route which you can define in any direction. This is points per segment. The interpolation method we can use. The full potential is for more accuracy. Otherwise, you can use the 1D or the 3D expansion method. For to solve the diagonal, it is the diagonal solver to solve the eigenvalues and eigenvectors. So you can use the full diagonalization solver or the iterative diagonalization solver. Here it is. For the iterative, you have to define the set range of Fermi level and the interior eigen strategy, which is shift and invert or the harmonic extract. Let's say if I wanted to proceed with the harmonic extract, and max number of iteration must be 100. Here it is. Similarly, you can calculate the Bloch state, chemical potential. Current density you cannot calculate at it is the bulk configuration, not the device configuration. So if you are going to set your workflow, if there is any error in your workflow, then it is going to indicate by this red cross sign. If you click here, it will guide you that what is the error with your workflow and how you can correct this. So let's delete this block. Yeah, here it is. Someone was asking about partial charge. So here you can see we have the block for the partial charge, but here you can see for the partial charge only trim absolute calculator are supported. So we can use the force field calculator. So this is our force field calculator. Here it is. So again we are getting an error. So let me select the potential set. So if we proceed with the force field calculator, we do have these potential set. Some of our theoretical base, some of our experimental base. So we do have more than 300 basis set, which almost covers all the periodic table or important structures. Although if we do not have this one, then you have the LCO calculator to generate your own potential set. So let's see. We can choose the Terpson AU 2012. So here you can see it is defining the from where which potential that we are using, and you all can also get the information from where we have fetched this. This is from the literature of this one. Here you can see the European Physical Journal. So now we have defined the force field calculator. The partial charge does not have any extent form. So here we have created a simpler workflow. Now we can do jobs as a script. Here you can see if you wanted to save your structure or the LCU calculator data, you can. But for now, we are just saving all the analysis part properties. If you click on OK, here you can see save. Yeah, here it is the part that I have left it out in the presentation. So to fire the job, you have these options. So if you proceed with the serial job type, then you are firing the job with the number of processor 1 and the number of thread is also 1. But if you wanted to manipulate, if you wanted to change the number of thread, then you can proceed with the second option in which you can manipulate the number of threads on per single processor. If you proceed with the multi-process parallel, then you can define the number of processors as well and the number of threads as well you can manipulate. Let's say if I wanted to proceed with the 3 and 6 number of threads. Yeah, this also depends on what computational depends on your system actually, how much processor and threads it supports. Click on add. Yeah, here it is our structure. Let's run the job. Now till the job is running, we do have some already simulated data which we can see. Let's directly start with some of the test cases now. So let's create the PN junction diode at the atomic level and how you can calculate the IV characteristics for that. So first we have to import the silicon from the database. Okay, it is the molecule. Here you can see this is the silicon alpha structure. These are the properties. Just double tap on it. Now we do have the silicon. To create the device, we have to do the surface clear. Here you can see. If you click over here, these are the Miller indices that you can define. So these are nothing but simply the vector propagator in which direction your structure must propagate to create the larger structure. This is something like that. If you click on next, these are the surface indices. You can change the magnitude if you want. Let me show you. Yeah. If you click on next, here you can define the thickness as well. Here you can see. If you click on finish, now we have created the bulk configuration. Now we can change that bulk configuration through the device configuration. Here you can see the option. Here you can directly search for any plugin tool. So yeah, this is our device. Here you can see this is the left electrode, which is the source as well. This region is left electrode extension. This is the central region, also called as scattering region. This is right electrode and this is the right electrode extension. Also, you can manipulate the electrode length if you want. Let's click on OK. Yeah, now we have created the device. If you wanted to do the doping, you can search for doping. Here it is. So you can select the region in which you have to do the doping. You wanted to do the doping, let's say. So it is bit roughly way. You can proceed with the select by expression. Yeah, here it is, select by expression. So this longitudinal vector is of C, then we can write C is less than 0.5 and click enter. Here you can see we have selected the left region only. If you click on add, here you can see we are defining the doping. So at the left region, we are doing p-type doping. Here you can see. Also, you can define the concentration and the unit as well. So we have done the p-type doping in the left region. In the similar way, we can write C is greater than 0.5, click enter. Now we can do the doping on the right side as well. Click add, yeah, and type doping that you wanted to do in the right region. Now we have done the doping as well. Also, if you wanted to introduce any spatial region like metallic gate or the dielectric, which is for the sometimes useful for to calculate the capacitance. Here it is the dielectric. So let me show you one. If you click over here, you can introduce the metallic region or the dielectric region, which will create the three probe device. So let me introduce the dielectric. If you click on dielectric, you can define its epsilon naught value, which is dielectric constant, which depends on the structure. If we click 4, 4 I think is of hafnium. So we have created the dielectric of hafnium, a kind of similar thing. Now we can define its length and breadth. On z direction, it would be 1, and on y direction as well. Yeah, here you can see we have created the dielectric, which is not much bit accurate. You can refer the literature or the your experimental data, then you can create the perfect structure. Currently, I'm just showing you an example that how you can introduce the dielectric as well. Similar way, you can create the metallic gate. So let me introduce the metallic gate as well. Here you can see. Yeah, here it is. But for now, we can delete these spatial regions as we are creating a two probe device. Now we can take that structure to the workflow. We can set the calculator. So here you can see if we are using the simple calculator, so it will show the error that is it does not support because it's the device configuration. So you can use the device LCO calculator or the semi-empirical device calculator. So let's proceed with the semi-empirical calculator. Here you can see you can choose the Hamiltonian parameter group. That is, this is density functional tight binding. NRL and other group also you can choose. Hamiltonian, this is the Hamiltonian or predefined function. This is the device algorithm. Here you can see for the equilibrium condition, we are using the Green's function, and for non-equilibrium Green's function, which is a finite device, also we are using the Green's function. Also, you can proceed with the sparse Green function. This is the contour integral. You can use the single or double, but as we can also use the single one as we have T2 probe device with the single layer as well. This is the Poisson solver. So we do have for the Poisson solver type, we have fast Fourier transform. Currently we are using fast Fourier transform 2D, which is for device configuration. You can proceed with the multigrade option. So by selecting this option, you can define the boundary condition along A, B and C direction, whether it can be the Dirichlet condition or the Newman boundary condition, right? So you can define the electrode voltages as well, which with this thing we also can define in the block of IV characteristics. Yeah, this is the checkpoint handler, which is something like for some bigger simulations, which takes even time more than 1 hour, 2 or even more than a day. Then you can enable this checkpoint handler to save your data for such cases like uh, power failure or that your system got crashed. Then you can that your data will be saved. Then you do not have to do the simulation from the starting point. Then you can use this checkpoint handler to do the simulation from where it ends. Now once your calculator is ready, we are about to calculate the IV characteristics. So let me search for the block. Yeah, here it is. Double tap on it. So you can define the gate to source voltage. Currently we do not have used any metallic region or the dielectric, so we can left out with the 0 0. This is drain source voltage. So let me define from -5 to 5. Here it is. Also, you can define the number of points. Let's say 20 points I want. This is the unit. Also, you can calculate the transmission spectrum. You have to define the energy range. Let's say, okay, by default case, we can proceed -2 to 2, and these are the number of points. For the k point sibling for this device configuration, we do have the list of point, one cost, pack grid, or the density. You can define. Also, for the RL shift, you can proceed with this. You can see the advanced options. Also, you can manipulate this. You can include this analysis like current density, electron density, external potential, total charges, molecular populations, etc. So once our workflow is ready, we can proceed with the jobs as a script. Click OK. Yeah, here you can see the previous job that we have simulated for the gold has been done, and it just take 18 seconds. Here you can see. So for this job as well, we can run the simulation. Here it is. Till the simulation is running, we can select. We can see the results that we have calculated previously. Yeah, here it is. Here you can see for the gold, as we do not have introduced any charges, so partial charge value we got 0. We were just taking the example, but this is how if you would introduce the spinotronics, then you can see any change in this value of partial charge. Although let me show you that how you can introduce the partial charge. Let me show you. Yeah, here it is our calculator. You can introduce whether the spinotronics to check the charge value. Also, this is something if you write like -1, then you are introducing the dangling electron in that structure. You can cross this one. So under the data, you can see the result. Let me show the silicon result first that we have calculated previously. Just a second. Yeah, here it is. The simulation for silicon that we have created. So this is something that you must have seen in many books. This is the forward region. This is the reverse region. Here you can see some distortions, which depends on the doping. Actually, this region is just showing that your structure got damaged at that much reverse biasing. Although you must have seen this kind of graphs in your books as well. This is the cutoff, and here, as we are moving high, we are getting a higher current value. Also, this is for gate source, but although we do not have introduced any gate source, so we will not get any graph. This is current scaling under the linear, and you can define the logarithmic as well. Here you can see, and the symmetrical logarithmic condition as well. So yeah, we have gone through the silicon device test case. Now let's do one more test case where we will see the molecular dynamics. We will do the molecular dynamics of a carbon nanotube by introducing any defect on it. So to create that carbon nanotube, we can proceed with first we have to create the nanosheet. Let's create the nanosheet. Now we can repeat the nanosheet. Let's say 10 times in C direction. Also, you can repeat in the similar way in A or B direction. Let's click on apply. Now we have to create some defect in that sheet. So we can use the geometry selector, in which we can choose the center of the region and then click on select. Now to create the defect, I can rotate these atoms. Here you can see the value under the x is 1. Here this you can see the graph. So we will rotate the atoms along x-axis 90 degree. If you click on apply, here you can see we have rotated this atom. So such defect that we see, these are called actually stone vase defect, stone walls defect. Now to create the CNT, that is carbon nanotube, you can use the wrap. Here you can see under the coordinate tools we do have the tube wrapper. So you can define the angle, that is 360. If you click on preview, yeah, here you can see we have created the CNT. Click on apply. So here you can see the defect as well. Now to calculate the properties, let's say if you wanted to calculate the transmission spectrum for that, then first we have to do the change this configuration to the device. Here you can see we are changing this bulk configuration to the device configuration. Now we can take this to the workflow builder. We can select the calculator as our structure is big, so we can choose the force field calculator as it will not take much time. So we can choose this one, and now we can calculate the transmission spectrum. Okay, so transmission does not support this one, so we can delete this calculator. We have to choose apart from the trimaxillary calculator. So for this device calculator, we can proceed with the semi-empirical calculator. Here it is. Jobs as a script. Okay. Add. Okay, although I have already have done this simulation before, so let me show you the results directly. Yeah, so this is the transmission spectrum that we get after the simulation. Here you can see, you can calculate the spectral current. You can define the left electrode potentials, right electrode potential. These are the chemical potentials, although the temperature also you can directly change. For example, currently it's at 300 Kelvin, that is of a drain side. So I can change it to, let's say, 1000 Kelvin. So you will see the change in spectral current when we are changing the temperature of right electrode. Similarly, you have this spectral conductance. This is the thermal current. In the same way, if you change the temperature of right or the left electrode, you will see the changes. Okay, I have write the 3000 by mistake, which is much higher. Yeah, this is the correct one, 1000 Kelvin. Here you can see. In the similar way, you can calculate the thermoelectric coefficients like conductance, Fettler's feedback, thermal conductance, ZT as well.
Tushar, just to interrupt you, you showed the
Yeah,
thermoelectric behavior. Could you please switch back to the same thing? Thermoelectric behavior of the
yeah,
material.
just a second.
So there are some coefficients, Peltier, Seebeck, and thermal and ZT values. Could you please a little bit elaboration how they were computed?
To see the what theory or the formula that this calculator is using, there are, you can directly refer to the manual. Let me show you. If you search for QuantumATK documentation, all the theory or the backend formula that it is using, you can see here. Let's see if you wanted to see, like for the Hamiltonian, you can see we are using the Concham equation. For the basis set, to calculate the electron density, we do have this one. All the theory you will get in this documentation page. You can directly search with the Synopsys QuantumATK or the QuantumATK documentation page.
Okay.
So yeah, I have shown you the maximum feature. Yeah, let me show you one more feature, that is of machine learned force field. We do have this thing. So let's create the different workflow. Yeah, here it is. So here you can generate the moment tensor potential by doing the moment tensor potential training. So you just have to select the configurations. So this is we are doing with the hafnium. So we do have to select the few structure, or the single structure will also work. So here you can see we do have this structure, that is orthorhombic structure of hafnium, and we do have the monoclinic structure and the cubic structure. More the number of structures are here, you are going to get the better accuracy. So once you have patched all the structures, then you can cross this option. Then after that you can define the calculator. These all are the parameters that I've already introduced already. And then after that, for do the machine learn force field, we do have this crystal training random displacement, which is for training of crystalline materials, which contains some small displacement, and with this anotropic strain, or the volume strain, or the large displacement, with the large displacement with anisotropic strain. Then we do have the scan over nonlinear coefficients, which is for generating a series of MTP fitting parameters to scan over different initial linear coefficients of the differential equation that it will generate. We do have this. After that, we do have the moment tensor potential training, which is for study of training and testing for the moment tensor potential. And it will collect all the data to generate the graph of like energy, forces, stress. So here it is. So we have created the simpler workflow. After simulating the job, let me show you the data directly that we have already calculated. Just a second. Yeah, here it is. This is the active learning graph. We can open with the moment tensor potential analyzer. Okay, I think this one. Yeah, after the simulation, you are going to get this data, which is of targeted value, that is of test energy and the train energy. So here you can see, using the machine learned force field, uh, you can calculate the potential sets in this way. Here you can see all the data as well. So now once we have this data, so how we can use this data for our better accuracy? Let's see. Let's say if you wanted to do the molecular dynamics for any structure, uh, let's create the structure. Let's create the hafnium itself, because we have the data for hafnium only. So here I have take the hafnium. Let's include the 100 atoms. Now click on build. Now if we wanted to do the molecular dynamics for this, you can take this to the job workflow builder. Workflow. Now we can fetch the block for force field calculator. Here it is. Now under this option, here you can see this is the option to use that MTP data that we have generated using machine learn force field. You can upload the that file here. So let me check for the file. Yeah. So the base data is of 29 feet. Open and click here. So now if you are going to do the any analysis, so let me search for any. Yeah, let's suppose if you wanted to do the molecular dynamics, or if you wanted to find the properties such as Young's modulus or the stress strain. So by the way, actually these are the methods for the molecular dynamics that you can use. NV, velocity, Wright, NV Beretson, Buisson, noise hover, Lagrange, or the stress strain analysis, etc. So let's proceed with the Beretson. Also the seeking you can define like reservoir temperature, heating, thermal coupling, target temperature. Also if you wanted to fix the center of mass, then you can. So let's say now we are calculating the molecular dynamics using this one. But what if we use the LCO calculator? If we use the LCO calculator with such bigger structure, so let's say if you wanted to calculate the number of atoms in this structure, if you just have to click over here on the I sign. So it contains 300 atoms. So for lower computational, it may take 2 or 3 days to compute the molecular dynamics for such bigger structure. Also, you can see other information of that structure, like its cross sections of different vectors or its primitive vector. But as we have generated the MTP, now it will take just few minutes, even few seconds for such bigger structure, and you are going to get the similar property that you will get for the LCO calculator or the plane wave calculator. So this is how you can use the machine learned force field to save your time and for better accuracy. So yeah, our workflow is ready. We can take do this to the jobs as manager, click OK. Now we can save the job. Here it is. So I have done the simulation for that thing previously as well. Let me directly check for the output. Okay, we do have the data, but not for the hafnium, but for SiO2. So here you can see we have done the molecular dynamics. This time temperature with respect to time or energy with respect to time. If you click OK, under the movie tool as well, you can see this is just the how the dynamics is changing. It is showing that, but the main data is here, like temperature with respect to time or the energy with respect to time. Also, you can include the energy density or the volume. Here it is. So this is how you can use the machine learned force field as well. So these are the some other different properties. Here you can see I have calculated the band structure previously for silicon as well, which is 3.3, which is very near to the experimental value. Here you can see. Also, you can export this data as well in the form of image, PDF, or the text file as well. In the text file, you will get all the x and y value respectively. Also, you can calculate the effective mass. This is the longitudinal effective mass, and this is the latitudinal one. So by defining this, you can calculate the effective mass for electron and holes as well. Also, let me show you a few more properties. Here you can see we have calculated the projected density of a state, and this is the grid value, which you can compare with the different methods as well. Let me show you for the kernel or the average method or the Gaussian method you can use. Here you can see. Let me show you the optical properties that also you can calculate. Here you can see under the x-axis we have energy, wavelength, frequency or wave number depending on the type. You can calculate absorption of light, refractive index, excitation, reflectivity. This is on y-axis. Dielectric constant, susceptibility, polarizability, optical conductivity. Here you can see. And if you wanted to focus on any particular part as well, you can do this thing as well with the advanced analysis tools. Let me show you with the wavelength. Yeah. Let's say if you wanted to focus on that particular region, then you have this zoom tool that you can use. Here you can see. Yeah. This is the sigma with respect to wave number. That is wave adsorption with respect to wavelength. So the tensor that we are currently using, that is a diagonal of the structure. Also, you can change this tensor value as well. Here you can see the tensor value. Susceptibility. Let's say if you wanted to just see along the z axis, then you can choose this one. Here you can see the susceptibility. Let me zoom in. Yeah, this is with respect to only z axis, but for the diagonal condition, we can select the diagonal only, like x, x, y, y, and z, z condition. So yeah, I have shown you the maximum feature of this software. Now, if you have any doubt, you can ask. The session is open for all. I have shown you the maximum properties, that how you can create your structure, create workflow, how you can set up all the calculations about the job manager, how you can simulate, etc. So now, till now, do you have any doubt?
Yeah, participants, if you have any specific doubt, then you can ask. We have the speaker.
Or if you want me to simulate a particular structure or the property that you wanted to see.
No, sir, can you tell me regarding the organic polymers? You have discussed mostly the inorganic polymers like metal and its source polymers. But what about the polymers? Those are from the natural sources like tragacanth, like your
Okay.
chitosan, like your casein. So how you one used to bring the molecules from which database? And can you show one demo for that? I shall be thankful to you. What parameters we can calculate in the like example is chitosan nanoparticle doped with a cancer drug for drug delivery or for drug targeting. What data we can get from the DFT study or from
Okay,
other
got it.
parameters? Can you please explain, please?
So may I take the methane, which is a simpler one, right?
Sir, my
May I,
question is that how could I draw the polymer first? Like a
okay, to
chitosan or
generate the
casein. So
polymer,
where can I
yeah.
apply? So yeah, take a polymer, please.
So in the workflow, you have this polymer builder. In the workflow, you can just type polymer. If you double tap on it, so to create the polymer, first you have to select the monomer. Let's see. Let's proceed with this vinyl monomer. If you click on add, also you can define the random polymer, that is for multiple polymers, also the alternating as well. This is the number of monomer per chain. This is the number of chain. This is the monomer flip probability, which is currently 1. But if you wanted to manipulate, you can. Starting and ending group also you can define. Here it is the polymer environment. If you click on add, you can fetch any structure which you intend to do. Let's say if okay, let me choose the simpler structure. Yeah, So this is the silicon that I have chosen. This is for the host configuration. Also, you can include any molecule. Let me include simpler one. Okay, you can proceed with any random one. Then you have to define the temperature and the molecular dynamics step for forced cap assimilation. Also the force field, which can be the OLPS A, OLPS mean universal reading, etc. After defining all this sequence, uh, you can cross. Now you have this block, which you can take to the jobs as a script. I'm not sure how much time it will take, but let me start the simulation. Polymer underscore result. Okay. So yeah, this is the way till the polymer is generating. It will take some time actually. But one thing you can do, these are my contact details. After this simulation has been done, I will share the result with you. You can just write my number. This is my email. Even after this session, if you have any doubt, all of you, if you have any doubt, then you can ask.
Sir, can
After
you
the
share
simulation, sir,
few?
I will
Sir,
share
can
the
you
result in the
share?
group. Yeah,
Okay, can you share few papers of this DFT relevant to the not the metals? Metals. I'm not dealing with the metals. I'm saying regarding the polymers for that natural polymers. You understand natural polymers for job
let me
loading or
directly.
job delivery. So in your software, people have used and they have worked on that. So I need few papers or reference to read your article. Can
Uh,
you share to the
Actually, under the
Nikhil sir and he will share to
sure,
us
sure.
in the
I'll
group?
share a few of the research articles with Dr. Ashok. I'll share that. So, since we
Mhm.
have a little bit time left, Tushar, could you please highlight regarding the software licensing and how to get it the software?
so it is the commercial software, and about the licensing, we would prefer to talk over the call only, right, sir?
I didn't get the thing. Could you please elaborate a little bit more?
Actually, we do have two type of licensing, that is of 1 year and the perpetual one,
Uh,
and it is the bundle license as I've already shown, like the 25 simulations that you can perform simultaneously. You can connect with the, even you can fetch the license type is floating. From the parent computer, you can fetch the license to the client machine if the systems are connected over the same LAN network.
okay.
So the 5 DFT simulation, 5 force field, 5 device, 5 material simulation, in total 25 simulations that you can perform simultaneously, whether on the local machine or the remote machine. So here you can see the option. You can fire the job remotely as well. These are the remote options.
Hmm.
Yeah.
Okay, so you
And
mean
about the
regarding
pricing,
the
these are my details. If you anyone wants to know about the pricing, I
oh,
will share the details as well. Yeah.
sure, sure. So, participant, I request all of you to please take a note of the contact details. If in case you want even further details, you can please contact to Tushar on his number 888-210-3961. One more thing, Tushar, can I share the recording with the participants so that the few more participants, I think they would be approximately 1,000, they can also see the recording part.
Yeah, yes, sir, you can.
Okay,
Even
dear.
though after this, if they have any doubt, I have already shared my contact details. You can email me. Email would be
That's
the better choice. You just
that's
have to write an email. I will clear your doubt.
okay. So, participant, if you have any more
Yeah.
questions, please ask. Otherwise, we'll thank the our speaker for giving huge time and elaborating a lot of properties which we can estimate using the quantum espresso. Indeed, we have bought this quantum espresso long back in 2015. If
Actually, sir, it's quantum ATK.
Yeah, QuantumATK, correct. So QuantumATK, we have bought the software in 2015 through IIT Madras. I think, but the major difficulty we faced, it has come with annual licensing thing. We every year we have to renew that. Am I correct?
Yes, sir. Actually, for 1 year license, it comes with the 1 year maintenance, and even for perpetual, it comes with the 1 year maintenance. But with the minimal amount, you can renew your license if you want it to be upgraded with the latest version.
Uh,
Otherwise, it is not necessary. If you are comfortable with the previous version,
uh,
so you don't have to buy the maintenance. But for the cases such as rehosting or any technical support, you must be under the maintenance only. Yeah.
Okay, dear. Okay, dear. I'll thank the speaker for delivering a wonderful talk on behalf of all the participants who are there, and look forward for few more interactive session like this. Thank you, Tushar.
Thank you, sir.
Yeah, yeah, we can.
And regarding that polymer, uh, I will share few publications with you, and then you can directly put in the group as well.
Sure, sure.
Or you
Otherwise,
can,
Dr.
yeah.
Ashok, you can just put up a mail to Tushar. He have given you the email ID. Just write a mail to him. Okay.
And even though you all can directly search for this documentation page, in which under the list of publications, you can directly write the keyword to search the particular publication. Here you can see if I just write polymer and the modeling and the dynamic physical properties for polymer models, biomolecular dynamics simulation, and machine learning, etc. You can find all the publications related to that using quantum ATK.
Sure, sure, sure. Tushar, these are the publication which cited the quantum ATK. Am I correct?
Yeah, these are the in which few of the simulations have been done by using quantum ATK. Yes.
Okay, okay. Fine. That's great. Thanks, dear. So we'll leave the session and we'll have the DFTG evening batch at 9 p.m. Thanks to all. We'll join today at evening 7 p.m. Thank you.
Okay. So thank you everyone for listening. Now,
Yeah, we can leave the session.
yeah. Thank you.